Hello calculus students. Today is a unit all about a variety of strategies for integrating functions that involve the trigonometric functions. We begin with a slide that reminds you of some identities that you should have seen in a pre-calculus or trig class. They will be very useful in this particular unit. We'll begin with the Pythagorean identities. Sine squared plus cosine squared of an angle is equal to 1. And then it has a companion version of it. This is the tangent secant version of Pythagorean identity. It's easy to get this second version by taking the first version and dividing every single term by a cosine squared of theta. Sine squared over cosine squared is tangent. Cosine squared over cosine squared is the 1, and 1 over cosine squared is the secant. So it's quite straightforward going from one to the other. Specifically, the versions of these identities that we will be using are this identity here after you solve it for cosine squared. So that would read cosine squared of theta is equal to 1 minus sine squared theta. We're also going to use this version when sine squared is isolated, right? So sine squared of theta can be found by doing 1 minus cosine squared of theta. And we're going to use the second where tangent is isolated. So tangent squared of theta is equal to secant squared of theta and then minus 1. The next one over here is the half or double. I call it the half/double angle identity. I think most books would call this just the half angle identity because the angle in question, which is 2 theta here, just becomes theta over here. So the angle cuts in half when you look at this identity from left to right. However, when you look at the identity from right to left, going this way, the angle doubles. The identities down here, typically the identities that you're seeing right here are the ones that they call the double angle identities because going this direction, the angle goes from theta to 2 theta, so it doubles. But I'm going to call these the power reducing identities because the real purpose we're going to be using these two identities for is because we have a square on a sine function that I want to be able to write this in such a way that we have no exponents other than 1 on the trig functions involved. This will make integration become a little bit easier. Notice how similar these two formulas are, the sine squared and the cosine squared. Both of them wind up producing a cosine of 2 theta, but the only difference really is right this sine right here. Okay, the first example I want to show you is using the power reducing identity for integrating sine squared. We're going to use this power reducing identity to get rid of that square. So it's equal to the integral of 1/2 1 minus cosine of 2 theta. Now if you want, you could factor the 1/2 out of the integral, or you could distribute it through the parentheses. I'm going to go ahead and distribute it. So I'm going to put a 1/2 minus a 1/2 cosine 2 theta. And then d theta. Oh, I don't know why I'm writing thetas. These should all be x's. Now we can integrate term by term. Well, the antiderivative of 1/2, so we have 1/2 x. And the antiderivative of negative cosine is negative sine, so it'll be sine 2x. But to reverse the chain rule, we have to divide by another 2. Well, there was already a 1/2 in front, so that should wind up becoming a 1/4, and then plus c. Now, technically, we're done. We have an antiderivative, but I'm just going to use the double angle identity to take this sine of 2x and turn it back into terms of the angle going back to just x. So that's going to be using this identity right here. And so we have 1/2 x minus 1/4, and then sine 2x becomes 2 sine x cosine x, and then plus c. And then, of course, we can simplify by multiplying the 1/4 and the 2 to make another 1/2. You could make the case that the last two steps I did were not necessary because here we do have an antiderivative, but there are times where it's nicer because this original problem started in terms of x. X was the argument of the trig function. It's nice to get an antiderivative where any trig functions that you have also have the same argument. Okay, let's go to the next slide. Sine cubed. Well, sine cubed involves a strategy of breaking the sine cubed apart by factoring. So we're going to do a sine of x times a sine squared. The sine squared, you have lots of options for using an identity on it. Going back up to our identities up here, for sine squared, you could use a Pythagorean identity or a power reducing identity, depending on what is going to be more useful to finish the problem. In this particular case, it's actually going to be better to do the Pythagorean identity as our next step. The sign that's in the front just stays, and sine squared is 1 minus cosine squared. One reason why I wanted to use Pythagorean identity instead of the power reducing identity is the mere fact that The Pythagorean identity doesn't change the argument. It starts at theta and ends at theta, but the power reducing identity doubles the argument. So it's nice to have an overall expression where the arguments of the trig functions, they're all x. Plus, you're going to see now that this is perfectly set up for just a classic u substitution. The reason I see a substitution being useful here is because the derivative of cosine of x, just that part, not the square, involves sine of x, which is a factor of the integrand. That's a hint that a chain rule has occurred. So I'm going to let u be cosine of x. The derivative of u is negative sine of x, and then the dx. Notice that we don't have a negative sine of x dx, but I can make it negative as long as I counter it with a negative. And now I can say that, well, this negative sine of x times dx together form the du. The negative outside the integral stays, and then this part here just winds up becoming 1 minus u squared. So our integral becomes this expression. Now I'm going to go over a habit that you should develop when you have negatives out in front of integrals. Those negatives tend to be problematic for students. Either students will forget to distribute them or they'll just forget them entirely. So I like to usually take care of my negatives right away if they're in front of an integral. If this was a definite integral, like say from 2 to 3, then I would make this positive and swap the 2 and 3. That's one property of a definite integral you can do to take care of a negative in front of it. Just switch the limits of integration. But this is not a definite integral, it's an indefinite integral. So instead I'm going to take care of it by distributing it through the integrand. So that gives me the integral we're doing now, just u squared minus 1 du. So the antiderivative from here is u cubed, and then put a 1/3 in front, minus, and the antiderivative of 1, don't say x, that's a common mistake. It depends what the differential is. If this is a du problem, then the antiderivative of 1 is u, and then plus c. And then finally, we're going to do our back substitution, right? All the u's we're going to change back to cosine of x. And so we have 1/3 of cosine cubed of x minus just cosine of x, and then plus c. And this is our final answer. Now I leave this to you to verify with a derivative. Don't forget to use the generalized power rule, the chain rule, and do the derivative correctly. But you should get to the point where when you do a derivative that you could express your answer, something like that, and then use the Pythagorean identity to go to that, and then go back to the original. Okay, next slide, sine to the fourth. Since we have a lot of options at our disposal when I have sine squared, it seems reasonable to want to split this up into sine squared, and then see what we can do from there. If I do a Pythagorean identity on just one of these, make this 1 minus cosine squared, and then think a u substitution again. The problem with this is that when u is equal to cosine of x, I only need one sine x here to create the du. But I have sine of x times another sine of x. I have too many sines of x's. So instead, I'm going to do the power reducing identity twice. So each of these sine squares will become a 1/2 times 1 minus cosine 2x. And since each of them will have a 1/2, I can multiply the two 1/2s and make a 1/4 and put that in the very front. So there's the 1 minus cosine of 2x from the first sine squared, and here's the 1 minus cosine 2x from the second sine squared. From here, I'm going to do some FOILing. I'm going to multiply this expression out. We do 1 times 1 is 1, 1 times, so we get negative cosine 2x. We get that again, and then we get positive cosine squared of 2x. The two middle terms are similar, and they can combine, and we have a cosine squared of 2x to work with. For the cosine squared, you actually want to do a power reducing identity again, this one. Now this angle doesn't have to be theta. It could be any expression. You could put a 3x there, as long as you put here twice that, so a 6x would go right there. So I can use this power reducing identity for cosine. Right here for the underlined portion, it's going to be a 1/2 times parentheses 1 plus the cosine of, and then double this angle. So it's currently 2x, so it needs to double the 4x. And then you end those parentheses and then our dx. Okay, so we're at this point. Now it's a good idea to help get rid of some of these parentheses. I mean, there's an implied set of parentheses around all of this anyway, with this 1/4 out front, and then you have this inner set of parentheses as well to be considering. I'm going to leave the 1/4 out of the integral, but I'm going to distribute that 1/2 and then do some simplifying here. So we're going to leave the 1/4 out, and then we're going to add 1/2 plus a 1/2 of cosine 4x. And then I'm going to combine the constants. 1/2 plus 1, that's going to give us a 3/2, or the 1 plus the 1/2 made that 3/2. Now I'm going to integrate. Now, because there's a constant in front, the 1/4, make sure you put your antiderivative in parentheses. The antiderivative of 3/2 is 3/2 x. The antiderivative of negative cosine is negative sine. To reverse the chain rule, the antiderivative of negative cosine 2x is really negative 1/2 sine 2x. There was a 2 here to begin with, so the 1/2 that gets generated is going to cancel with that 2, leaving really just sine 2x. If you're not sure you did that right, just take this term and differentiate it and see if you get that term. The derivative of negative sine 2x is negative 2 cosine 2x. And then over here, the antiderivative of positive cosine is positive sine, and we have to divide by a 4 to counter the chain rule from the 4x. So there's already a 1/2, another 1/4 will join that, so we have a 1/8 of sine 4x. Now it's probably a good habit now to do some double angle identities on both of these and try to get this problem back to simple x, but I'm going to go ahead and not bother with that this time and just leave our answer pretty much like you see it. I mean, one thing you could also do is distribute this 1/4 through, so we would have 3/8 x minus 1/4 of sine 2x plus 1/32 of sine 4x. So here's an answer that doesn't need any parentheses, and we'll call that one good. All right, as you can anticipate, we're just going higher and higher powers until you can pick up on a pattern. So let's do some pattern recognition, starting with sine squared. With sine squared, I just did the power reducing identity once, and that put it into a form where I could integrate and finish. When it was sine cubed, I saved one sine. This is called saving a sine, and the sine squared I converted to cosines using Pythagorean identity, not power reducing. And then I did a u substitution to finish the problem. Back to the sine to the 4th, I had to do power reducing twice, once here, once there, but then a third time later right there. So I just had to do a bunch of power reducing identities to eventually get this to the point where I could integrate all the terms one at a time. Sine to the 5th. When you have an odd power of a sine, save one of the sines and then break up the rest of them into groups of sine squares. Now, because we have a single sine over here, we're going to be able to use Pythagorean and Pythagorean identities and then do a u substitution on the cosine of x's that are produced. So we wind up getting an integral of sine of x times 1 minus cosine squared of x and times another 1 minus cosine squared of x. And now we want to do the same substitution we did before. Let u be cosine of x. The derivative will be negative sine of x dx. Well, I have the dx and I have the sine, but I don't have the negative, so just put it there and counter it with a negative in front. And this integral now will look like the negative in front stays. This will be a 1 minus u squared, another 1 minus u squared, and then the negative sine x and the dx become the du. Okay, now we just have to do some foiling and then integrate it. Foiling in here, we get 1 minus u squared, so minus 2u squared, and then plus u to the 4th. Now once again, I have a free floating negative in front, and I don't like to have that there, so I'm actually going to distribute it now and write this as negative 1 plus 2u squared minus u to the 4th. Now I'm going to integrate term by term. Keep in mind I'm integrating with respect to u. So we have negative u to begin with, plus 2/3 of u cubed, minus 1/5 of u to the 5th, plus c. And then of course the final step is the back substitution. Each of these u's goes back to cosine of x. So negative cosine of x plus 2/3 of cosine cubed of x, minus 1/5 of cosine to the 5th of x, and then plus c. And there it is. All right, this pattern that we're picking up on will continue. If I wanted to do sine to the 6th, I would do sine squared, sine squared, sine squared, and change each sine squared, use the power reducing identity, and then FOIL, and then keep doing power reducing identities as necessary, eventually to the point where I could just integrate all the terms that are present. When this goes to sine to the 7th, I would keep one sine off to the side, and then you'd have sine squared, sine squared, sine squared, and each of those sine squares I would change to 1 minus cosine squared. Do the Pythagorean identity on each of those, and then do a u substitution. Now, all the things you see here that I'm doing for powers of sine are mimicable for powers of cosine, which I don't have in the lecture, so I will leave it to you to try these same slides, but do cosine. And you can check your work using online integral calculators and the such to see that you're doing it right. Let's move on to different kinds of trig. Tangent squared. I'm going to use the Pythagorean identity for tangent squared. Tangent squared is equal to secant squared of x minus 1. It turns out this is very useful because the antiderivative of secant squared is one that we should recognize right away as an antiderivative of tangent, because the derivative of tangent is secant squared. And then the antiderivative of that negative 1 is going to give us that negative x, and we're done. How about tangent cubed? For tangent cubed, I'm going to split apart that tangent cubed into a tangent and a tangent squared. And let's use the Pythagorean identity on the tangent squared, which is secant squared of x minus 1, I'm going to distribute this tangent of x and make this into two different integrals to solve. So there's one integral, and then minus, and then the second integral will be when I distribute the tangent here, so just integrate tangent. It's pretty common that sometimes you want to distribute and approach this as two separate problems. You know, when you're integrating a sum or a difference, you can integrate them term by term. And it's helpful to write this as two separate integrals entirely, because it may be that you'll use one strategy for this one and a different strategy for this one. You don't necessarily use the same one strategy for the entire problem always. Now I notice that when I look at tangent and secant squared, I'm thinking u substitutions. If I were to let u be the secant of x, then the derivative of that would be secant x tangent x. Well, this is fascinating because there's actually two secants here, so I could split them apart. One of them I could call u, and the other one I would need to group with the tangent x and the dx to create the du. So this would actually be a useful substitution for this part. But notice we have some options in this one. It's also true that if I let u just be tangent of x, then the derivative of tangent is secant squared of x dx, which I have sitting right there. So this would just be a u and a du. For this second integral, this is when we wrote that as sine over cosine, and then I let u be the denominator, the cosine. And we wound up getting natural log of secant or negative natural log of cosine as antiderivatives. So I'm not going to repeat that process here. So the u substitution is only being used for the first integral, so it winds up being an integral of u du, and then minus, and then here I can actually go ahead and just finish that integral. The antiderivative of tangent is natural log of absolute value of secant. And then we get a u squared over 2 is the antiderivative of u, and then minus a natural log of secant. And now that I've finished all the antiderivatives, it's a good time to throw in that plus c. And then we just have to do our back substitution, change that u to a tangent. So we have tangent squared of x, that's all over 2. And then minus a natural log of secant of x, and a plus our c, and we'll call that one done. If you had done this problem here with the original substitution I said, which was let u be secant, and then let the secant tangent dx become the du, then you would have had an answer that was a secant squared of x over 2, and then the rest would have been the same. And you would have said, wait a minute, are they both right? They look different. The reason why these are both acceptable is because the Pythagorean identity for tangent squared, right, I could write tangent squared as secant squared of x minus 1. And then when I divide that by 2, I divide both of those by 2. But this extra 1/2 could be absorbed in the plus c. Both of these answers represent the same infinite family of antiderivatives. But let's go ahead and just leave tangent squared 1 as my final answer. Okay, so I want to discuss how to do just the antiderivatives of secant and cosecant. If you will recall, this is still two gaps in our knowledge of how to antidifferentiate some basic functions. There is no particular method that I would use to get this answer, but one strategy of finding an antiderivative is to do guess and check. This turns out to be the antiderivative, and we're going to prove it's true by doing the derivative of this. And just a quick reminder, don't forget that if you're differentiating the natural log of absolute u, that the derivative is u prime over u. All right, so the derivative of natural log of absolute secant x plus tangent x, we put the derivative of the argument, so the derivative of secant is secant tangent, plus, and the derivative of tangent is secant squared of x. Combined, those two things are the derivative of the argument and then over the argument. All right, so we get to this point right here after doing the chain rule. And notice that there's a secant in each term of the numerator. So we have secant of x can be factored out, leaving a tangent x plus a secant of x, which is exactly what's in the denominator. So we have this cancellation of these terms, and that leaves us to just secant of x, confirming that the derivative of this function right here will give you just secant x. For cosecant, the antiderivative is the natural log, and it's going to be effectively this same answer, except the co-versions, and also it'll be subtraction. So it'll be the cosecant of x minus the cotangent of x. And I leave it to you to verify the derivative of this answer would in fact lead to just cosecant of x. Another acceptable answer, which you could also prove through derivative that you sometimes see, is the negative natural log of, and now you just do this exact answer here, but the co-version. So natural log of cosecant x plus cotangent of x. Try either one of these, differentiate this or differentiate that, whichever, and show that the derivative eventually simplifies to just cosecant of x. And we can now go back to this derivative and antiderivative sheet and put in some answers here. Let's do secant first. Natural log absolute value of secant of x plus tangent of x. And the antiderivative of cosecant is the exact same but coversions. And if you do the exact same, put a negative in front. Or the other option was doing natural log of absolute and then do cosecant of x but minus cotangent of x. Either one of these for antiderivative of cosecant is acceptable. So that really only leaves these two blanks here. If you recall from our last unit, I showed you how to do arctangent and said that it can be done similarly for these two. So I still leave that to you to fill those in on your own. But just for the sake of completion, I think I would like to show you the answers you should get. And we get, for the arcsine, an antiderivative should wind up being x times the arcsine plus the square root of 1 minus x squared, and then plus c. And the one for arc cosine is going to be effectively the same thing, but an arc cosine, and there'll be subtraction between the terms. It's going to be x arc cosine of x minus square root of 1 minus x squared, and then plus c. Okay, and then that completes everything that's in this list. Okay, next one, secant cubed. Secant cubed is actually going to wind up being one of our trickier integrals to do. It's going to involve several strategies to get through this one, and either you can remember how to get it when you need it, or you can just memorize the results once we have it. I leave that to you to make that decision, although my recommendation would be once we get this antiderivative that you memorize it, because it's going to surface in multiple contexts. Let's begin the secant cubed by breaking it apart into a secant times secant squared. The very next thing I'm going to do here is an integration by parts, the table method. So I'm going to create a little table over here off on the side. We're going to have a differentiate column and an anti-differentiate column. Okay, I'm going to put the secant in the differentiate column, and in the anti-differentiate column, the secant squared. Don't forget we need the extra column over here that we'll put the signs in. And then I'm going to do only one extra row and then force stop the table. So the derivative of secant is going to be secant of x tangent of x. And the antiderivative of secant squared is tangent. And now we have the plus minus. So we're going to do a diagonal alignment, that's done, and then a horizontal alignment that needs to be integrated still. So we get the orange alignment gives us a positive secant x tangent x. And then the red alignment gives us a negative and integral. And then we multiply the red alignment, we get secant times tangent and times tangent. So secant tangent squared. Okay, now I'm going to use the Pythagorean identity on this tangent squared. We have a secant x, but then the tangent squared is going to become secant squared of x minus 1. I'm now going to distribute this secant. So we have a secant cubed of x minus secant of x. Then I'm going to break this integral up into two different integrals. This will, because there's a negative in front, it's going to have to distribute the negative as well, so be careful about that. There's going to be a separate dx right here. Instead of subtraction, write that negative distributed, so we're going to have plus an integral secant x dx. Okay, now keep in mind that, follow these equal signs back to where we started. We started with this integral. So I'm going to put that context back into play here. We're trying to do the integral of secant cubed here. And this is the statement that we've produced so far. Do you notice something? This is an alligator swallowing its tail situation. The integral I'm trying to find showed up again right here, but it's a negative copy of it. So I can actually take this and add it to both sides so that they cancel on this side of our statement. Leaving only this integral left to be done, and the antiderivative of secant, we just did that. That's natural log secant plus tangent. So where does this take us? Well, over on this side, we had a secant cubed plus another secant cubed integral, so we have two of them now. And this is equal to secant tangent, and we have plus the integral of secant, and that we can do. So plus natural log of absolute secant of x plus tangent of x. And then now's a good time to put a plus c. Our final step, of course, is next to get rid of this 2 by dividing both sides by 2. So after I divide both sides by 2, that's going to put a 1/2 in front of both of these. You can divide the c by 2 as well, but all constants divided by 2 is still all constants, so it absorbs into that plus c. Here we have an antiderivative of secant cubed. Again, I said secant cubed is going to be an antiderivative that you're going to need to do a few times. I personally just have this one memorized. To help you with memorizing it, notice that the secant x tangent of x is the derivative of secant, and the natural log of secant x plus tangent x is the antiderivative of secant. When you add them together and then divide by 2, or in other words put these 1/2 right in front of each, then you get the antiderivative of secant cubed. So let me say this in words. The antiderivative of secant cubed is the average of the derivative and antiderivative of secant. in my opinion, this is worth making your own line down here, right? Putting a secant cubed and then putting in that result right here and just commit it to memory. Here's an integral secant x, cosecant x. The purpose of this problem here is to illustrate a new strategy. If you have sines and cosines, that leads to certain strategies. If you have secants and tangents, that leads to certain strategies. If you have cosecants and cotangents together, that leads to certain strategies. But here we have sort of an intermingling of different kinds of trig functions, a secant times a cosecant. So one strategy you can also do is just turn everything into sines and cosines and go from there, see what happens. For example, the secant is 1 over cosine, and that cosecant is 1 over sine. And then you multiply those together, and you get 1 over sine x cosine x. When I see a sine times a cosine, I can use the double angle identity here. You could divide that 2 to this side, so if the 2 is not there, you could do an identity that sine x times cosine of x is equal to 1/2 of sine 2x. All right, that seemed useful. And then when I invert and multiply, I could write this instead as the integral of 2 cosecant of 2x. Now from here, I know how to integrate cosecant of x dx. What about cosecant 2x? We'll just do a simple quick u substitution on that 2x. The derivative of 2x is just 2, so times dx. So this 2 and this dx become the du, and we really just get an integral of cosecant of u du, which is in our list of memorized antiderivatives. Remember, you had 2 options here. I'm going to go with the natural log absolute cosecant of u minus cotangent of u. And then the final step, of course, is the back substitution. And we were able to work out an antiderivative for this problem. But the whole purpose of this example was to show that sometimes it's better to convert the trig functions into sines and cosines and then see if there's any sort of strategy that can emerge from that. Here we have a mixture of sines and cosines already. When you're multiplying powers of sine and cosine together, you're going to see a very similar strategy to what we did earlier when I was just doing sine cubed. If you see one of these powers is odd, they don't both need to be odd, but at least one of them does. Focus on any of the powers that are odd, in this case the sine, and save one sine off to the side, and then convert all the remaining sines to sine squares. But now I'm going to do the Pythagorean identity on just that part right there. But when you do this, we're perfectly set up to do a substitution on the cosine. Let u be the cosine of x, du will be the negative sine of x dx. There's the sine of x, there's the dx. We do need a negative, so I'll put those negatives there. And I'm ready to convert this into an integral in terms of u. So we have a negative integral of 1 minus u squared times another u squared, right? That cosine squared becomes a u squared. And then we have the du. I'm going to distribute the u squared and distribute the negative together at the same time. So this winds up being an integral of u to the 4th minus u squared du. Right? Distributing a negative across there allowed me to switch the subtraction. Right? If you do like negative distributes, and it really winds up just being b minus a. So then this gives us 1/5 u to the 5th is an antiderivative minus 1/3 u to the 3rd plus c. And the final step is the back substitution to go back to cosines. And we are done with this one. If these powers had been reversed, if it was sine squared and cosine cubed, then I would have saved a cosine and then converted the remaining cosine squared to sine squares using Pythagorean identity, and then let u be sine of x. But the key is, look to these 2 powers, and if one of them is odd, you can do a strategy like that. But what happens when they're both even? When all the powers on the sines and cosines are even, then we're going to mimic what we did when it was just sines and not a mixture of sines and cosines, which is use the power reducing identity multiple times. Well, each of them is going to produce a half, so there's going to be a 1/4, and then the sine squared became 1 minus cosine 2x, and then the cosine squared involved the 1 plus cosine 2x. Each of them had a half, of course, but those halves combined to be a 1/4, which is in front now. And then do some FOILing next. We got 1 plus cosine 2x minus cosine 2x, so the 2 middle terms cancel, and then minus cosine squared. And then from here, we're going to have to do another power reducing identity on this. That's going to produce a 1/2 times a 1 plus cosine, and then double the angle from 2x to 4x. I'm going to distribute this negative 1/2 and then combine the constants. All right, so we're going to have a 1 minus a half essentially, so that's just going to produce a half. And then distribute that, and we get minus 1/2 cosine 4x. And then anti-differentiate. I'll leave the 1/4 out in front this time. The antiderivative of 1/2 is 1/2 x. And then the antiderivative of negative cosine 4x is negative sine 4x divided by 4. There's already 1/2, so we need a 1/8 there in front, and then plus c. And then, of course, I think the last step I would do is distribute this 1/4, which I won't bother doing here in the lecture. But By the way, those sine cosine strategies are summarized in our last slide for the lecture in this table. Right? If m is odd, then you can follow these steps. If n is odd, you can follow these steps. If they're both odd, then you can do either approach. But if they're both even, then you just want to do the power reducing identities, repeat as needed. The last class I want to discuss is what happens when you have powers of secant and powers of tangent. So we're going to take a look at an example of that and then just give a strategy after that. I actually might do a few examples on this slide beyond what's actually written here, just so you can see the different strategies. So we have secant cubed, tangent cubed. I'm just going to see what happens if I let u be the secant of x. Well, then the du would be secant x, tangent x, dx. So I'm going to make that du by taking one of these secants and one of these tangents to make a du. So this secant cubed I'm going to break up into a secant squared times a secant, which I'll put at the end. The tangent cubed, I'm going to do something similar. I'm going to make it a tangent squared, and then the extra secant and tangent I'm going to push off to the side, right next to the dx, right, so that I can see what part of this is going to become the du. Okay, now that leaves me over here. This part's just going to become u squared, but this one, there's no help here with my u. But if I do Pythagorean identity on that tangent squared, change the tangent squared to secant squared minus 1, and then the rest of this here gets repeated. Now I'm fully prepped to convert entirely to u's and du's. Right, I see a u squared minus 1, and then I see a du sitting right there. So the integral of u squared times u squared minus 1, and then du. All right, to finish from here, I'm going to distribute this u squared across, so I get u to the 4th minus u squared du. Integrate those separately, so 1/5 u to the 5th minus 1/3 u cubed plus c, and then a back substitute. Right, each u is a secant of x. So we have 1/5 of secant to the 5th of x minus 1/3 of secant cubed of x plus c, and that's a good final answer for this one. Okay, what really made this one possible to do was the fact that the power on tangent was odd, so that when I saved a tangent off, I also needed to save a secant, but I was trying to construct this ahead of time, which means that working backwards, I need to have a secant x, tangent x make my du. I need everything else to be convertible to secants. And if the power on tangent initially is odd, like it is here, and you pull one tangent off to the side to help make the du, then the remaining tangents will be even, and that can be converted easily to secants using Pythagorean identity. Hence, this substitution will finish out the problem. So you'll follow this basic model that you see here if you see an odd power on tangent. Who cares what the power on secant was? But if the power on tangent is odd, you can do this. Well, let's do next, right next to this, one that I'll make up just so you can see some variety. Secant to the 4th of x dx times tangent squared. What I just said worked when tangent had an odd power, but this tangent has an even power. So instead, I'm going to wonder what happens if I let u be tangent of x and see what I would need to construct a du. Well, the derivative of tangent is secant squared. So I need a secant squared times a dx to make the du. What I have is secant to the 4th. I have more than enough secants. I just need 2 of them to make the du. I'm going to take that secant to the 4th and break it apart, so there's a secant squared and then the tangent squared. And the other secant squared I'm going to push off here to the side next to the dx, right? So I can clearly see the du sitting right there. Prepping myself to do a u equals tangent, but I have secants and tangents still here. I want to turn everything to tangents, so that remaining secant squared is where you want to use your Pythagorean identity. And according to the Pythagorean identity, secant squared is the same thing as tangent squared plus 1, and then times another tangent squared of x, and then times the secant squared of x dx. And I'm perfectly prepped now, since u is about to become tangent. I'm going to have a u squared plus 1, a u squared, and that's going to be a du. So u squared plus 1 times a u squared times a du. Distribute the u squared through the parentheses, and then integrate term by term. We get a 1/5 u to the 5th plus a 1/3 u cubed plus c. Back substitution. This time the u's are all tangents. So we get a 1/5 of tangent to the 5th of x plus a 1/3 tangent to the 3rd of x, and then plus c. And we'll call this one done. This strategy works every time the power on secant is even. Because if it's even, you're going to need a sine squared to make the du. If you take sine squared away from an even, you're going to have an even a number still here, which you'll be able to successfully convert to tangents using Pythagorean identity, and then go with this substitution. And then as a final case, okay, let's do an integral of secant tangent squared. So the two strategies I just illustrated do not apply here, because for the first strategy, we needed tangent power to be odd. For the second strategy, we needed the secant power to be even. Well, here we have neither of these are true. We have an even on tangent and an odd. There's a 1 there on secant. In such a case, the strategy will be convert everything into secants and then go from there and see what happens. So we're going to start off with the Pythagorean identity on that tangent squared. Tangent squared is equal to secant squared of x minus 1. I'm going to distribute the secant. So we've got a secant cubed of x minus a secant of x dx, and then integrate all these secants. Well, to integrate secant cubed and integrate secant, remember, we got to use some prior results. We'd already learned how to integrate these. Secant cubed, the antiderivative of that was the average of the derivative of secant, which is secant x tangent x, and the antiderivative of secant, which is natural log absolute secant x plus tangent x. And then minus the antiderivative of secant is just natural log of secant x plus tangent x. And technically we're done, but notice that these two are similar. I have a half of a thing minus 1 of that thing. That takes me to negative a half of that thing. So I could write the final answer as 1/2 secant x tangent x. Right, this first term doesn't change, but the next two terms combine to be minus 1/2 natural log absolute secant x plus tangent x. And this is a good place to stop this one. Okay, these examples here illustrate a few strategies, 3 different strategies, depending on what the powers on the secant and tangent were, which are summarized in this table on your last slide. Right, if the power on the secant is even, then save a secant squared, convert the other secants to tangents using Pythagorean identity, and then let u be tangent of x and go through the motions of that substitution. If the power on tangent is odd, then save a secant tangent, convert the other tangents to secants using Pythagorean identity, and then let u be secant x, and then go through the motions of that substitution. If neither of those are true, in other words, if m is odd and n is even, then the strategy is to convert all the tangents to secants and then go from there. All right, so these strategies are going to take some time for you to practice, and that efficiency will come through practice.